So Steve Sherwood is our next lecturer. Steve is a CI in both of our Centres of Excellence, and he's going to start with waves and teleconnections, but he's covering quite a lot for us.
Yeah, maybe too much.
No.
All right, now I need to put this on, don't I? Because we're being recorded.
Yeah, if you want to move around.
Yeah, all right. So, oh man, how do I get this? I'll just put this down here. That's easier. Okay. So can everybody, does this come through all right? That's good. Okay, good. So I also didn't do this talk on the plane here. I couldn't have, because I'm actually talking today about a subject that's not really something I think about all the time in my own research. And so some of you probably know more about it than I do. So this will be a journey. Maybe we can, when it comes to questions and answers and discussion, people can jump in if there's things that I didn't make clear and so on. Maybe we can get some help from Michael Barnes over here, who's going to be talking next. But the idea is that if we're thinking about weather and climate and how they interact, to me, waves and teleconnections really seem to be central to that question. And so, for example, this is a study that I just ran across recently by Boers et al., where they used machine learning to try to figure out how weather in different parts of the world was being influenced by precursors in other parts of the world. And they come up with a lot of crazy images like this one, where the patches all over the world that are tied to what's happening in India. I don't know, I'm not going to defend any of their conclusions or anything, but what's interesting about this is that you've drawn a lot of great circle paths which they attribute to Rossby waves in the sort of discussion of their paper. They don't actually look at Rossby waves in the paper, but clearly these are on people's minds when they're looking at teleconnections. So we should probably look at Rossby waves. And the first way that some of you might have seen them is that you can even see them in a tank. So how many people here have played with a fluid tank like the one we're looking at here? I know some of you have. We sometimes do them at demonstrations for students. So this is a fluid tank that's chilled in the middle, meant to emulate a hemisphere of the Earth. It's rotating, the camera's rotating with the fluid, so that's why the fluid doesn't look like it's rotating, but then there's a barrier at the bottom, which, let's see if, what happened? Oh, it's still playing? Okay, this is strange. All right, okay, never mind. Anyway, there's a barrier here. The movie's not playing on my device, but it's still playing there, so I guess it's all right. Which is kind of generating a Rossby wave, which you can then see propagating around or moving around in the tank. So this is pretty cool. We can see these things even in a physical device. And you can also see them on the Earth. So this is satellite imagery looking at water vapor in the upper troposphere, which is a great way of visualizing the winds on the Earth. And you can see a lot of turbulence, a lot of clouds. If you look around the southern hemisphere here, you can see waves amplifying. And one thing that you might notice, there's a cyclone going across there. One thing you might notice is that the fluid acquires spin a lot of the time, and you can then see that spin maintained as the fluid is carrying it along. So there's a lot of spinning going on, and the spinning seems to have a life of its own. And that's going to turn out to be really important in understanding the atmosphere. So the outline for this talk is, I'll give you a little bit of introduction, which I've kind of already done, and then we're going to introduce some equations, and then talk about Rossby waves, which are these really kind of diabolical and hard to understand waves that are really important. So we'll see how we go with that. And the very first thing we have to cover is hydrostatic balance. So this is just a statement that the pressure is a relationship between pressure and position in the fluid. It's telling you that in a hydrostatic balance, the pressure anywhere will be proportional to the total mass that's above that point. So we've got a pressure of, we could say 5 here, because there's 5 layers of bricks above it, and the same thing here and here, and well, down here we've only got 4 because there's only 4 stacks of bricks. Okay, Now, if the bricks were accelerating up and down, this wouldn't be true. For example, if I came along and I suddenly pulled the table out from under the bricks, the pressure would immediately go to 0, and the bricks would start accelerating downward. So we're talking about something that's not accelerating up or down. And in the atmosphere, this is a pretty good approximation on most length scales. Okay, certainly the scales that we're going to be talking about today. So we'll be assuming that the pressure is hydrostatically balanced. So if the fluid has a slope to it, like this, the highs, high pressure locations, and the low pressure locations are going to be areas where the fluid is higher or lower, and also where the pressure is higher or lower. And if this were a fluid rather than bricks, we would be seeing a gradient in pressure horizontally, right? Because it's high here, higher there than it is there. So there's a horizontal force that would be acting. Now, in bricks are solid, they can withstand shear stresses, but a fluid couldn't. So you'd start to see flow in that direction, which would try to equalize out this unsustainable sort of pressure gradient. Okay, so that's the force on the fluid that we're going to be considering today. Now let's see how this works. What happens if I go, oh, that's interesting. It saves all of my stuff. Okay. So, so that's great. That's our force, pressure gradient force. And we've got that right here in our equation of motion. This equation here is F equals ma written for a fluid. It has to hold for every piece of fluid all the way in 3 dimensions in the fluid and for all the time. So it's hard to think about solving an equation in a medium like that, but that's what we have to do. I've mentioned already the pressure gradient force. There it is. The term over here on the left is the acceleration of a piece of fluid as you move along with the fluid. So how is its velocity changing? So there's the acceleration. But that's the acceleration that you would see if you're an observer standing on the Earth, in your reference frame standing on the Earth. But the whole Earth is turning, so that's not actually an inertial reference frame, which means F equals ma doesn't really work. So we have a fudge factor here, which makes it work, which is the Coriolis term. That, of course, is the acceleration of a parcel of an object that's moving at a steady speed, so that in the rotating frame it doesn't look like it's accelerating, but because of the Earth it actually is accelerating, and that's the acceleration that it really has that you can't see because you're standing on the Earth. So you need to add both of those together to get the true acceleration in an inertial reference frame. Okay, so we call this the Coriolis acceleration. Whoops, oh damn it. All right, well, that's all right. We'll just put that there. If you're not used to vector notation, there's the same thing written out as 2 scalar equations, one for the velocity u and one for v. So we're using a coordinate system x and y, and we've got velocities u, v, just like that. Okay, so that's our notation, our coordinates. So this v here is the vector velocity, and k cross v is just saying at right angles to v is the way the Coriolis acceleration operates. So we've got a u here and a v there, and vice versa here. I will, as people typically do, just for the sake of being able to think about it better, speak of a Coriolis force, which is a force that we imagine exists in order that F equals ma works in our non-inertial frame. Okay, mathematically it's the same whether we consider it acceleration or a force, but I'm going to speak of a Coriolis force. This second equation here is called the continuity equation. I'm imagining most of you have seen these equations before, so we're going pretty fast. If you haven't seen them, this is going to be tough, but I'm assuming most of you have. So this is just telling you that if your fluid is coming together in the horizontal direction, because this v here is just the horizontal velocity, if it's coming together, it has to be going out the top or the bottom, because you can't, or the density has to be changing, okay? So that's why the rho is in here. And so that's just conservation of mass, and that's basically the foundations of the equations that we're going to need. Now, there are a couple of situations that can arise that are worth considering. One of them is if you have flows that are very rapid, like waves in your bathtub or a tornado or something, which spins around very fast, then this Coriolis term isn't really important, and you have what we would call a cyclostrophic balance between a fluid that's constantly changing its direction or sloshing back and forth and the pressure gradients. Okay, that's what happens in water waves and in a tornado. Another situation we might imagine is where the fluid is changing gently enough that the time derivative term is small. And then you just have Coriolis forces balancing pressure gradients. And that is what we're going to be mostly talking about today. And it's called geostrophic balance. So the way that would work is we would have a fluid velocity that's maybe like that. And if we were in the southern hemisphere, we would, if we're in the upper troposphere, we have a pressure gradient force pushing us toward the pole. And then we have a Coriolis force, or what we perceive as a Coriolis force, pushing us back to the equator. So I'm just walking along like this, and I've got two opposing forces pushing one in each direction, and therefore I just keep going in a straight line with my inertia. I don't turn at all. That's geostrophic balance. Okay, and I'll just mention that there's something called the Rossby number, which is the ratio of this term to that term. So if it's small, then we're in geostrophic balance. That's how you can tell. And the Rossby number, I should say, depends not only on the shape of the flow, but also the speed of the flow. If we double, for example, the speed of a vortex, this first term actually becomes 4 times as large. So these equations are not linear, and the Rossby wave depends not only on the scale of the flow. It tends to be small for large flows, but it also has to be slow enough to be in geostrophic balance. Okay, I think that's all I wanted to say there. Whoops. Yeah, okay, there we go. So, okay, so those equations are nice. If we wanted to solve them for general cases, we would have to code it up on a computer and burn lots of CPUs. But there are various simplifications that have been devised to help us understand what's going on. And one of those is the shallow water system. So I already mentioned that we're going to be making a hydrostatic approximation, so we'll keep doing that. But we'll also imagine that we have a fluid of uniform density and that it's in a very thin layer, so like that. Now, if you're used to thinking about the atmosphere, you might think, how on earth can you assume it's constant density? The atmosphere goes through, many orders of magnitude of density change. But believe it or not, it actually kind of works. We'll just bear with me. You could think of the ocean as having nearly uniform density. Even there, oceanographers typically want to use at least 2 layers. But we can start by thinking of 1 layer, and we can get pretty far. And if we make these 2 assumptions, then our equations get to be a little bit simpler. One thing is, if you think back to the layers of bricks here, we can directly relate changes in height to changes in pressure just through the density of the fluid, which is now constant. So we can just replace our grad P with a gradient of the height of the top of the layer. So H here, if we have, I've exaggerated that, but this here is H, okay? So we have H, it can vary spatially. The changes in H are small because it's a thin fluid, and it's got some mean depth H naught, okay? And the divergence equation also becomes simpler because rho drops out of it. If rho is the same everywhere, you can just divide by rho and you're done. And then you get this. So it's getting simpler, but we still have three unknowns. We have U, V, and H that we have to worry about. And sorry, we'll be able to, we can change this. Let's see, I think, yeah. We'll be able to get rid of W here, because you could probably see that in this system, if the velocity is converging together, h is just going to be getting bigger. So we can actually put in here, I think we can change this to a kind of dh dt term. Okay, so what we're now going to do, now that we've defined our shallow water system, is notice that there are self-consistent solutions to this system where the velocity is the same all the way through the depth. Because we assume that the density was uniform and that it's hydrostatic. And therefore, if you think back to the stacks of bricks again, the pressure gradient horizontally was the same at every level, right? Because it was all bricks. So every time you go down a certain amount, you increase the pressure by the same amount. So all the forces are going to be the same through this shallow layer. And therefore, we would expect that the velocities could all end up always being the same. There's nothing that would ever be different, okay, at different levels. So there are not necessarily the only solutions, but the only ones we care about, where the velocities are the same throughout this shallow layer. So they're going to look like this. And if we just imagine that we have, let's see here, a wave here, like this, okay, what's going to be happening is, because the fluid is converging the way I've drawn it, it's also going to be going up right there, and that means the wave's going to be propagating which way? To the right, yeah. So our wave is going to move to the right if this is all the stuff that's happening. Okay. What else did I want to say here? All right. I've got the word barotropic here. That's just a fancy word that we use that means that the flow is doing the same thing through the whole layer. So we have a barotropic solution to the equations of motion. And that's very important because we've now gone from a three-dimensional to a two-dimensional system. If we just know the velocity everywhere as a function of x and y, and h as a function of x and y, we're done. So we've made it simpler. Okay. Oops. Okay. So we would like to solve this, and one thing that I want to point out now, having done all that we've done, is it turns out, if we think back to our movie and noticing that things that were spinning seemed to be carried along, we might be interested in looking at the spin of the fluid. So we're going to define something called the vorticity, which is right here. And it's just the curl operator applied to our two-dimensional velocity field, drawn here, if you haven't seen curl before. It's just measuring how much the fluid is spinning. It's just the rotation rate of the fluid. Okay. And, whoops. And what we want to do is get an equation for that. And so the way we do it is we start by taking the curl of our momentum equation. I'm not going to do all the math, but I think Michael might do some of this later. So you'll see it again. But the idea is that you have to manipulate the equation that we've got there. And if you do that, and you plug in also the continuity equation, you will find out that d by dt of c plus f over h equals 0. Okay? And, when you take the curl here, by the way, here you're just going to get the time rate, the derivative of the curl. The curl of the derivative is the derivative of the curl. Take the curl of that, it's going to go away because it's a gradient, curl of a gradient 0. This is the term that ends up producing a little bit of mess, which you then have to clean up by bringing in the other equation. But ultimately, you get to this. So what is this telling us? It's great. It's telling us that there's some quantity in the fluid that never changes, according to these assumptions that we've just made. As the fluid moves around, it doesn't change. Okay. And this thing in here, whoops, is is the potential vorticity. And it may look scary, but it's actually, if you took physics and learned about conservation of angular momentum, then that's all this is. Okay? So this first term here, the vorticity, I should specifically say is the relative vorticity, because it's the vorticity, again, in the coordinate system that we're using where we're standing on the Earth. And F, the Coriolis parameter, which we saw before, but I didn't say what it was, F equals 2 omega times the sine of the latitude, is the local horizontally projected spinning rate of the Earth itself. Okay, the effective spinning rate of the Earth itself. So if we add that to the relative vorticity, which is the spinning that you can see if you think the Earth is stationary, it gives you the total spinning, which we call the absolute angular momentum, or absolute vorticity of the fluid. So this sum here is the absolute vorticity. That one there is the relative vorticity. Okay, so this is the total spinning rate of the fluid. Now you might wonder, why is there an H underneath? Well, I was hoping there would be a chair here that I could sit on and spin myself around, because I used to do this when I taught this subject, but we haven't got one. That's okay. But most of you have probably seen figure skaters where they're spinning around. I'm not going to do this because I can't figure skate. But when they bring their arms in, they start spinning faster, right? And so the angular momentum of a spinning cylinder, if you think back to your physics, is proportional per unit mass is proportional to the square of the radius, or in other words, to the area of the cylinder. The cylinder gets bigger, and it has the same rotation rate. It has a lot more angular momentum. So anything conserving its angular momentum, if you reduce its radius, it's going to spin faster. If you increase its radius, it's going to spin more slowly. Well, what we're doing here is we're writing our equations per unit mass of fluid, and it's sitting in a layer that's this thick. So if it pulls into a smaller radius in exactly the same proportion, it's going to get taller. So basically, whenever the fluid gets taller, it spins faster. Whenever it gets shorter, it spins more slowly. And this ratio here just tells you that. So this is really just a statement of the conservation of the local angular momentum about the local vertical in the fluid. We will be talking later about the angular momentum of a whole ring of fluid around the Earth, which also is conserved in the absence of friction. But this is just the local spin that it has. Okay, so there's our potential vorticity. And if Michael will be talking more about this later, so you won't be done with this. All right, so this is great, but the problem is it's only one equation, and we got still three unknowns. We still got, they're hidden in there, we still got U, V, and H. What do we do? How do we solve one equation and three unknowns? We can't. But what we can do is we say, okay, well that was good heuristically, but let's go back to these equations. Let's try to simplify things. So what if we make F a constant? This is one thing that we could do. In fact, I just told you F is 2 omega sine latitude, but let's forget about that and just say it's a constant. Then we can go back and do the same equations, or same manipulations, take the curl, take the divergence of the equations to get some new equations for the spinning rate and the divergence. And then it turns out, if you then do another step and you integrate them spatially, you get equations for yet two more quantities. I found this really annoying when I was learning fluid mechanics. Why do they have to have all these bloody quantities? But it turns out that this is how you get separable equations that you can actually solve. And if you integrate them horizontally, then you get two more equations for the stream function and the velocity potential. And stream function is worth mentioning. If you have, a velocity field that looks like that, okay, it's going to be faster. If these are pressure contours, I meant for these to be pressure contours, and this is geostrophic flow. Oh, damn it. All right. If my pen comes too close to the screen, it suddenly does something. So these are like streamlines, but they're also lines of constant pressure in a geostrophic system. And what the stream function does is it kind of labels these 1, 2, 3, where the rate of increase of the label is proportional to how much flow you have transected as you ascend in stream function. So somewhere you define the stream function to be 0, which is actually arbitrary, and then you count from there to get from anywhere else in fluid to there. How much crosswise flow do you have to ford or cross to get there? That's the stream function. So it's just a label, and along a line of constant stream function, that's the way the flow is aligned. And then velocity potential is analogous, except in the other direction. So it's very much analogous to an electrostatic potential if you've thought about that, and where the velocities are like the field lines, electric field lines. So the velocity potential is just how much headwind would you have to fight against to get to this reference point here, from wherever you actually are in the fluid. We're not going to use velocity potential anymore today, so don't worry about that, but stream function does come up. So I thought it was worth telling you what it is. So if we do this integration and we get equations for these things, they turn out to be what you might recognize as wave equations. They're second-order differential equations. And when if any of you have taken differential equations in school, you know that the way of solving differential equations is you have this thing, and then you receive divine intervention, and it tells you what solution to try, and you put it in and it works, okay? There's no really other way to do it. And so if you see this and you say, aha, it's going to be this. It's going to be a wave-like solution. Sine and cosines is all this is. If you're not familiar with imaginary numbers, it's just sines and cosines. And what you want is to plug this in with some coefficients that you invent, k and omega. K is, as you could probably intuit from here, is the wave number, so it's the number of wiggles per unit distance at a particular instant in time. Omega is there we go again. Omega is the number of times the field oscillates per unit time at a given position in space. Okay? And you don't know what they are, so you just put them in as variables. And you also could have an amplitude out in front, which ends up not mattering because it's a linear equation. And then you chuck it in, and you solve it. And what you want is for all the sines and cosines to cancel out, which they do, and you end up with an equation relating the coefficients that you put in. And that's what is shown here, and it's called a dispersion relation for waves. So it tells you how the k's and omegas and stuff have to be related. And it looks a little messy here, but we're not interested in the omega. There's an omega equals 0 solution to this. You can set omega equals 0 and it worked great, but like who cares? So we don't want that one. Or if everything here in parentheses is 0, then it also satisfies the dispersion relation. And that means that omega squared equals this. So, okay, that's interesting. Well, you're probably more familiar, or at least when I came to this subject, I was more familiar with light waves, sound waves, water waves in your bathtub. All of those have a really simple dispersion relation, okay? Those simple waves have a dispersion relation that says omega equals ck, right? Where c is the velocity of the wave. So if it's a light wave, c is the speed of light, and then frequency and wavelength are related by this simple formula. All the waves, no matter whether they're radio waves or gamma rays, they're all going at the same speed of light. We don't have that here, unfortunately. We sort of do. If this term would just go away, then actually we do, because then you can just say omega equals plus or minus, let's just write it approximately, plus or minus the square root of GH0 times K. That actually does look like our simple wave dispersion relation. So, and we can see that we would get that. I shouldn't have crossed it out because you can't read it. But we would get that if omega and K were really big. And so what we get is a dispersion relation, which I can graph here. that looks like that. Now, I'll leave a little space for my equation. The simple dispersion relation would look like that. So if they were purely like, the simple waves we're used to, it would be the dotted line. But in fact, it departs. When we start having the wave being very slow, it starts to be affected by the rotation of the Earth, and its dispersion relation starts to change. And eventually we can get to something where the omega is not 0, but k is 0. And that's basically just fluid going around and around in a circle being pushed around by the Coriolis force. Okay, which is not, I guess it can happen in the ocean. You don't see it in the atmosphere. Not very interesting. But if the waves are fast enough, then they don't feel the rotation of the Earth, and they're just like the simple waves we're used to. So that's kind of comforting, I think, to me. And these are called buoyancy waves, or we call them gravity waves. Physicists probably don't like that because they have something else that they call gravity waves. But in our field, either of those terms is fine. And they just involve pressure gradients alternating with flow accelerations. Okay? And to get them, all we had to do was neglect the variations of f, which eliminated some nonlinear terms in the equations, made it easier to solve. So, great. All right. Oops. Yeah. Now, I told you we're solving equations in one thin layer, which we're assuming is uniform density. Clearly not a great approximation, especially for the atmosphere. You can add more layers. And so you could have 2. Here we have 2. And then you can get what the oceanographers will call internal waves, or atmospheric scientists will more often call baroclinic waves, where you have opposite things happening in the 2 layers. So we could have velocities that look like that, okay? And then you would have no deformation of the upper surface, but big deformations of some intermediate surface. So the waves are all trapped inside the fluid. And you can have that as long as you have 2 different densities, a light fluid sitting on top of a heavy one. So it turns out that if you have this 2-layer system, it still supports the same waves we had before, with both layers doing the same thing together. That's a solution. That works. So everything we learned before, it still applies. But then you have the baroclinic modes, where they're doing the opposite. And for the waves that we just saw before, they still have buoyancy waves. But you need to, and the maths is the same, except you need to use this reduced gravity where the restoring force on the wave comes from the difference in density, which may be very small. So if you have 2 fluids whose density is only maybe 1% different, you're going to get a wave that has a G prime that's only 1% as big, which means it's going to move 10% as fast. And that's kind of what we see with baroclinic waves. They move a lot slower, but they have similar dynamics. Okay, so that's just an aside, so that keep in mind that when we're talking about one layer, it applies to more layers, fluids with more layers. Okay. So, all right, well, that was nice. That was for setting f constant. What else can we do? We can go back to the equations again, and we can say, okay, well, let's try to do something a little smarter. What if we allow for the Coriolis force to have some variation with latitude, but we're just going to linearize it? What if we try to linearize the whole system? So we can linearize this. And what if we take note of the fact that for a lot of the flows we're interested in, they're very close to geostrophic. So what if we linearize about departures from geostrophy? It turns out that this turns out to be a super powerful thing to do. And it gives us what's called quasi-geostrophic theory. I'm not going to go through all of quasi-geostrophic theory. This was the basis for weather forecasts that were done back in the day by Rossby and Charney before they had the kind of computers that we have now. Gives you a really simple system. But what I'll point out is that the reason this is so powerful is that you can define the stream function that I mentioned before just in this geostrophic way, geostrophic stream function. And it then turns out that all three of the variables that we're trying to solve for have a pretty direct relationship to the stream function, okay? The h is just proportional to the stream function because, remember, since our velocities are always perpendicular to the pressure gradients, we end up with the vorticity being proportional to the Laplacian of the stream function, and we end up with the height being proportional to the stream function itself. So if we knew the stream function, we could get back all the other variables, okay, in this approximate approach to the problem. So this turns out to be super useful, and we can then again go and we can solve the linearized differential equation for stream function that we get, which I'm not going to write here, but I think you'll see it later today or tomorrow. And we again get the dispersion relation just like before, but it looks different now because it's a different system. We're getting some new stuff. And it looks even uglier than the last one, I'm afraid, but that's the way it is. We're now finding that it doesn't look anything like this dispersion relation for simple waves. In fact, approximately omega equals this, and I should say that now we have to worry about the direction of the wave. So before, when we set f constant, it removed any directionality to the background system, right? Those buoyancy waves are the same no matter what direction they're propagating. Not true here. We've now found a new class of waves that depends on what we call the beta effect, or the fact that the rotation rate of the planet varies, or that you see where you are varies with where you are. We've got this new class of waves because of that. And so k, little k, is now the component of the wave number in the x direction, and little l is the component in y direction. So k and l are like a vector pair that tells the direction of the phase speed of the wave. And our dispersion relation takes the little k and divides it by the sum of squares of both of the k's in the denominator and multiplies by beta approximately. There's also, as before, we have this extra term in the denominator which is sometimes important, and that's the Rossby wave number. So what is that? The Rossby wave number k is the reciprocal of the Rossby radius of deformation, or it's related, it is, the reciprocal of the Rossby radius of deformation. And that, you can think of that distance as the distance that the gravity waves can travel in one inertial period, where the inertial period is 1 over f. So you're a gravity wave, you're moving along, and if you only move for a few hours, it's fine. But if you keep going too long, the Earth is sort of rotating under you, and eventually you start turning, right? And so that introduces a limit to how far gravity waves can have influence. Their sphere of influence, in effect, is the Rossby deformation radius. So that's appearing in this dispersion relation. Now, if we're considering waves that are much shorter than that distance, then we can make the approximation shown here. And in the atmosphere, it's going to turn out that for most of the waves of interest, this is a good approximation. And in some atmospheric science texts, like Holton, they'll just go to this approximation right away, whereas oceanographers will always keep this term, because oceanographers turn out to have to deal with a lot of internal Rossby waves where the radius of deformation, remember what I said about the propagation speed of the internal waves? They're really slow. So the Rossby radius of deformation depends on whether it's an external or internal wave. It depends on the vertical mode in general of the wave. It doesn't depend on any of the other aspects of the flow. It only depends on the latitude and that vertical mode. And so for internal waves, it's very short. And so if you're interested in internal waves, internal Rossby waves, which the oceanographers are, then you do need to worry about this. And you're going to have two kinds of waves. You're going to have long ones and short ones. So the if I graph this out for a wave moving in the x direction, it looks like this, okay, where it asymptotes to 1 over k, but for very small k, it's linear. And the sort of the lurking around here is the Rossby deformation radius. So what is this telling us? One thing is that the speed of the wave, which is just omega over k, for our simple waves, this was the dispersion relation for the wave itself. And so the speed was just c. And this is the phase speed of any wave, is just the ratio of the frequency to the wave number. So if we imagine that this is a wave where L is 0, so we just have minus beta over k, it's, instead of beta k like it was for the simple ones, beta divided by k. So that means that the speed is going to be proportional to 1 over k squared, because it's just coming from this formula. Whoops. This formula here. It's not listening to me. So that what that means is that if the wavelength of a Rossby wave drops to half, its velocity drops to a quarter of what it was. The short Rossby waves are going to be really slow, long ones really fast. Very strange, not like the waves we're used to where they all go at the same speed. And it means a packet of Rossby waves is going to change its shape as it moves along. Okay. And also it means that if the wave is traveling with a non-zero L, its relationship between omega and its k is going to be different. And we'll see how that works as we go along. But these are the sort of diabolical Rossby waves that have this phase speed that is very different for different wavelengths. Now, okay, so, and I forgot to say one thing, which is that there's a minus sign here. Let's see if this works now. Yes, good. Minus sign right there. And k squared is always positive. So the ratio of omega to k is always negative. Always negative, which means that the phase speed of Rossby waves is always to the west. Now, remember what the phase, we're going to be talking about something called the group velocity in a minute. The phase speed or the phase velocity from our, where did we get omega and k? We got omega and k from here. So that tells you that that velocity is the velocity that the undulations appear to have as the wave evolves. Okay, so wherever the peaks and troughs are now, look at where they are in 10 minutes, and that difference is what we call the phase velocity. And it's always to the west with Rossby waves. It can be in different directions, but it's always going to the west. So why is it always going to the west? And why are the small ones short? Or why are the short ones slow? There's a kind of an argument you can make, which imagine that you have some vorticity somewhere. Okay, so we have a vortex like this, and we're also in a situation where you have a strong Coriolis force there and a weaker Coriolis force there. This is again in the northern hemisphere because most of the materials I have to work with are from the northern hemisphere. I'm from the northern hemisphere, and a lot of the people who figure this out, we're all living in the northern hemisphere. So you'll have to bear with me. Sometimes I'll switch. But imagining we're in the northern hemisphere, we have this situation where the planetary vorticity has a gradient, and we have a vortex sitting there. Now what's going to happen is this vortex is going to bring air down over here, which has this high F, and it's going to bring some air up over here, which has this smaller f. And so what you're going to have is an augmentation of the vorticity in this area and a depletion of the vorticity in this area over here from that advection of planetary vorticity. So you're taking spinning air, bringing it down. And if you flip this in the other hemisphere, It's just the mirror image. You get the same thing. And so if you wait, where are you going to see this vortex in the future? It's going to be farther to the west, right? Because you've added vorticity there, subtracted there. Your new maximum vorticity is going to move westward. This is the phase velocity of a vortex. And it's basically the explanation for why short Rossby waves move to the west in terms of their phase speed. For the long waves, it's a little bit different. I'm not going to go through that argument, but it's a similar idea, except that for long waves, the relative vorticity associated with wave becomes very small because the length scales are so big, and you end up having a balance between changes in the thickness and changes in the planetary vorticity. But otherwise, it's a similar idea, and it also ends up being westward. So vortices tend to move westward. This applies not only to Rossby waves, by the way. Tropical cyclones tend to drift westward, even though they're often embedded in a westward moving flow, but they'll actually move faster than the flow, and it's for the same reason. So if you see vortices sort of drifting toward the west, this is why they're doing it. Okay, so why are the long ones drifting faster? Well, if you think about how this argument works, the bigger the Rossby wave, the less vorticity it takes to displace it, because it's got less vorticity in it. It's bigger length scale, same, let's say it has the same amplitude, but a longer length scale, that means the vorticity anomalies are less. So it's actually easier to get it to move. Let's see. Yeah, so you can thereby understand why the long ones would move faster. Okay. And you can see this in weather maps. So again, Northern Hemisphere, sorry. This is from Wallace and Hobbs. Great textbook that I've been using for a long time. So they've drawn helpfully on here. This is a map over North America of the flow. And you can see there's this big wave. And the big wave just kind of sits there, right? If I just drew a line through this big wave, this is 12 hours, this is plus 12 hours, plus 24, plus 36. Sorry, I'm not drawing very well on the screen. But it's 4 snapshots that are 12 hours apart. And this big pattern is basically standing there. Now remember, there's a big velocity along these constant height. This is 500 millibar height contours. And the velocity is parallel to those. So there's a jet going from west to east, easterly jet. Now I've just told you that the phase velocity of all Rossby waves is to the west. But that's relative to the medium in which the wave is sitting. They're all Doppler shifted because they're all in a flow that's moving to the east. So if the wave is fast enough, it can stay in place and the air just goes past it, right? But if it's slow, it's going to get pulled backward. So what's happening is this big Rossby wave is basically stationary over this 36-hour period. But you can also see these little, well, they're drawn on here as fronts. Okay, these are shortwave troughs. They're places where the curvature of the flow is tighter. And there's one, sort of over North Dakota or so at the beginning, and then it moves, and by the end, it's gone past the Great Lakes. And then there's another one which they've identified up here in northern Canada, which by the end is now where the other one was at the beginning. So these little kinks in the flow, which are basically short wavelength Rossby waves, are being pushed along by the flow, and they're only slightly, fighting back a little bit, but they're still getting mostly affected by the flow, whereas the big one is standing there. So you can understand the evolution of weather maps already by thinking about these Rossby waves and how they propagate. Let's see how we do. I started at 1/4 When did I start? I think I started at 1/4. Anyway. 1/4. Oh, wow. I've already been going almost an hour? Okay. All right. Okay. So far I've been talking about Rossby waves that are traveling westward, phase speed. and sitting there on the jet, which is nice. But it turns out that Rossby waves can carry energy and momentum and information in any direction. And they do that because they have a group velocity. Okay? So how many people here have learned about group velocity before? 2/3 of you, maybe. Okay. So this is really tricky, but the way the phases move doesn't necessarily tell you where the energy and the information and the momentum are moving, and that's what really matters for teleconnections. Okay? If you want to imagine that something happens here, launches a wave, which then blows the doors open or something, it's the information and energy that has to get from here to there to do that. And in Rossby waves, the energy is traveling in a different direction than the phases, which is quite confusing. And you can work through the math and take the derivative of the dispersion relation that we had before, and you get kind of a messy, ugly-looking thing. But there's a simpler way of keeping track of it, which I like better, and that is if you draw it on a plane the way it is here on the right, you can take your vector for the phase velocity, and that's in black. So here's a few examples, 3 examples, and it will turn out that the group velocity makes twice the angle with east as the phase velocity. So there's this angle, and if we go double that, around there, whoops, I went too far. That's the group velocity, which is shown here. Okay, and same for these other waves. So whatever angle you make, double it, and it gives you the group velocity. That doesn't tell you the speed, and you'll notice that the speed of the group velocity can be quite different from one wave to another, but it at least tells you the direction. So if we think about this, it means, first of all, it means that the group velocity can be in any direction because we're doubling the angle. So we're starting with waves that are where the phase velocity is always in here. If we double that, we can get anything 360 degrees. But it also means, for example, if we had a wave coming from Indonesia down to Australia, bringing information, affecting our weather, I'll turn the same as you guys, the wave fronts would be doing this, even though the information is coming down. So it's very strange, but that's the way they work. So I think that what's brilliant about this is everybody thought that Michael Jackson just sort of invented this great dance, the moonwalk, but actually he was demonstrating Rossby waves. So if you watch carefully, the phase velocity is going to stage right, but the group velocity is going to stage left. And then the best thing about it is that at the end, he shows the Rossby wave breaking. Okay, so he was a genius and also a great science communicator, which nobody knew. So Rossby waves are really diabolical. This is just what they do. So how do you cause one? This is a graph of what you get if you have flow over like a seamount or a mountain. And what the mountain does is it compresses the air and thereby, making the cylinder bulge out. And it changes that takes whatever absolute momentum it has and reduces it, right? Which in the northern hemisphere means it's going to start having an anticyclonic relative vorticity, which means it's going to turn to the equator. So there it goes, turns down to the equator, and then it overshoots, then it goes woo, 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 like that. And so a Rossby wave has lateral motions, and one of the ways of driving them is if you have flow over topography. Another way is if you heat the atmosphere, which then squeezes the upper part of the atmosphere and gives you something similar in the upper troposphere. Okay, so that's what can cause them. So we know where they can go, we know what can cause them. And now I'm going to show you, I don't know if any of you went to this, I don't know if this is going to work. Oh, this may not work. I was hoping I could show you this movie. How many people watched this movie? Because I sent it around ahead of time. Oh, very few of you. Oh, I knew it was going to be that. Okay.